So beginning the section of 4.2, we're first going to define what partial generalization means. So we say that a formula B is a partial generalization of a formula A if B is A prefixed by 0 or more universal quantifiers with any bound variables. So what does this mean? This means that a partial generalization of A is simply A in which you add any number of quantifiers we want with any bound variables at all. So let's look at some particular examples to make this more meaningful. So if we take A to be the first order formula P equivalent to phi of x, then any partial generalizations, so some partial generalizations of this formula include the formula itself, or adding a quantifier over x, or adding a quantifier over x and a quantifier over y, or adding any number of quantifiers to this statement, including for all y, p equivalent to phi of x. This for all x shouldn't be here, but any order in which we want. So this is the same as this as well. So anyway, adding any collection of quantifiers ahead of this A is defined to be a partial generalization of that original well-formed formula. Okay, so now that we've defined partial generalization, we are able to define the axioms of first order logic, and note that we're going to denote this by lambda sub 1 to distinguish this from the axioms of Boolean logic. So, the logical axioms of predicate logic consist of all possible partial generalization of any formula in the following forms. So, in addition to all of the statements or formula I'm going to list, here we can add any collection of quantifiers we want with any bound variables. So, the first type of axioms we have are all tautologies. So remember from the last video, tautologies in first order logic are those well-formed formulae in which their abstractions are tautologies in Boolean logic. So in particular, all tautologies in Boolean logic are going to be logical axioms in first order logic. So again, in particular, since all axioms of Boolean logic are tautologies, then we're simply adding more axioms to our original set of axioms to define first order logic. And remember, to any of these tautologies, we can add any collection of quantifiers. Okay, so now we get into more specialized axioms, which involve our new connectives and new well-formed formula defined within predicate logic. So the next axiom is the axiom of specialization or substitution, and it essentially says that if we can quantify over A, and we know that is true, for example, then we must have any instance of A is true, right? If A is true for every x, then we could substitute for x any other term, and that will make A also true. So this is the specialization axiom or substitution axiom, which may be quite familiar to you, right? I think this is one of those rules of inference you used in Math 1019, so hopefully that's coming back to you. Our third and fourth types of axioms involve quantifiers as well. So axiom 3 tells us that if we quantify over an implication, this implies that we can quantify over each formula first and then take their implication. So we'll look at a particular example of this type of axiom in class so that you can see why you would take it to be true, so why this is an axiom. The fourth one is a bit more straightforward, so we can spend some time talking about it now. So this states that A implies for all x. A is true whenever x is not free in A. So what does that mean? So essentially this seems a little bit funny, because if A is true, we can't necessarily quantify or say that A is true for every x, but we can if x is not free in A. So remember that if x is not free in A, either it doesn't occur in A, So then quantifying over x simply, adds no meaning to our statement here, because if x doesn't occur in A, then whatever we're quantifying over has no impact on A. The other case is simply that x does occur in A, but it's bound. So that means that it must be in the scope of a quantifier over x. So that means that A already is a general statement over x. So this additional quantifier here simply is redundant, right? We're simply saying for all x, something happens. So we can simply disregard this additional quantifier. So that's what this axiom is saying. Axiom 5 is our identity axiom. So it simply identifies that x should be equal to x for any variable x. So that one should be straightforward to believe. And finally, we have a Leibniz axiom for equality, which tells us that if two terms are equal, then if we substitute via term substitution into the same formula, then these formulae should be equivalent. So it's sort of a relationship between the equality of terms and the equivalences of well-formed formulae in which we do this substitution. So we'll look at particular instances of some of these axioms and identify when instances are actually these axioms and when they are not. Okay, so next we want to look at our first order rules of inference, and essentially these are the same as our rules of inference for Boolean logic. So in particular we have equanimity, just as before, except A and B now can be any first order formulae in predicate logic. And this you will recognize as Leibniz, except now we're going to call it Boolean Leibniz, or BL for short, because we have to be a little bit careful about C. So we need to specify that this holds as long as P is not only fresh, but is also not in the scope of a quantifier in C. So you may recall, if you read about substitution, that we have to be careful about capturing variables in quantifiers. So if a particular variable is meant to be free and not quantified over, and then we simply substitute it into a formula in which it now gets captured by a quantifier, or simply we quantify over that variable, then this changes the meaning of the well-formed formula and can simply make our equivalence not true anymore. So by adding this condition into and calling this Boolean Leibniz instead of strictly Leibniz, we're ensuring that there won't be any captures. And we'll talk a little bit more about captures in class, particularly when we talk about how to define substitution. Okay, so now that we have an idea about our axioms and our rules of inference, we can define theorem calculations or proofs. So as before, we're going to let gamma be any given set of formulae. These are going to be our assumptions, and then we define a theorem calculation from gamma, or a gamma proof, as any finite ordered sequence of formulae, just like before in the Hilbert-style proof, that can be written following the following rules. So, as before, we may write a formula from lambda 1, the axioms of predicate logic, or any of our assumptions, those well-formed formulae in gamma, and at any step, and then we may write the denominator of an instance of an inference rule, either EQN or Boolean Leibniz, provided all formulae in the numerator of the same instance have been written in a previous step. So this is exactly the same formula as for theorem calculations in Boolean logic. So we'll use Hilbert-style proofs again. And keeping with the same terminology, a proof from gamma is called a gamma proof, and any formula A that appears in a gamma proof is called a gamma theorem. Alright, so I look forward to meeting you next class to provide some more details about substitution and the axioms and how to begin doing some elementary proofs.